Picture this. You wake up tomorrow morning, step outside, and discover that every ocean on Earth has turned to solid ice. The equator, where tropical beaches once welcomed sun worshippers, is now a frozen wasteland, stretching endlessly toward horizons of white. This isn't some distant science fiction nightmare. This actually happened to our planet not once, but multiple times. And the secrets buried within these global freeze events might hold the key to understanding not just where we've been, but where we're heading. Today, we're going to explore 3 mind-bending revelations that will completely change how you see our planet's history. First, I'll show you how scientists recently discovered that these global freezes weren't disasters at all, but Earth's way of performing a complete planetary reset, wiping the slate clean for entirely new forms of life to emerge. Second, we'll dive into the shocking evidence that complex life, as we know it, might never have existed without these frozen catastrophes, that every animal on Earth today owes its existence to these periods of global ice. And third, I'll reveal the most unsettling part. The same mechanisms that triggered these ancient freezes are stirring again, and the signs are all around us if you know where to look. What I'm about to share with you comes from decades of research, from ice cores drilled in Antarctica that preserve atmospheric snapshots from 700 million years ago, from rock formations in Namibia that tell stories of oceans turning to slush, and from recent discoveries in Siberian permafrost that are rewriting everything we thought we knew about these events. This isn't just ancient history we're talking about. This is a preview of what could happen again, and understanding it might be our only chance to prepare for what's coming. Let me start with something that will immediately grab your attention. In 2023, researchers at MIT made a discovery so shocking that it took them 3 years to publish it because they couldn't believe their own results. They found evidence that during the most recent Snowball Earth event, approximately 635 million years ago, the ice sheets covering our oceans weren't just thick, they were over 2 miles deep in some places. That means if you were standing on what we now call the surface of the Atlantic Ocean, you'd be looking down at a wall of ice taller than most mountains, stretching all the way to the ocean floor. But here's where it gets really interesting. Within that ice, perfectly preserved, like insects in amber, they found something that shouldn't exist. Microscopic organisms that had not only survived the freeze, but had actually evolved during it. These weren't simple bacteria clinging to life in some deep-sea thermal vent. These were complex, organized communities of microbes that had figured out how to thrive in conditions that should have been absolutely lethal. They had developed entirely new ways of processing energy, new methods of communication, and most remarkably, new forms of cooperation that would later become the blueprint for multicellular life. Think about what this means. While Earth was locked in a frozen death grip that lasted for millions of years, life wasn't just surviving somewhere in the margins. It was innovating. It was preparing. It was using this planetary timeout to develop the biological technologies that would eventually give rise to everything from jellyfish to dinosaurs to us. This discovery completely flipped our understanding of these events. For decades, scientists had assumed that Snowball Earth periods were evolutionary bottlenecks, times when life barely scraped by until the ice finally melted and things could get back to normal. But what we're learning is that these weren't setbacks at all. They were incubation periods. Earth was essentially putting itself into a deep freeze to allow life to completely reinvent itself. Now, you might be wondering how we know any of this. How can scientists peer back hundreds of millions of years and read the story of a frozen planet? The answer lies in some of the most ingenious detective work in the history of science, and it starts with something called a cap carbonate. When you look at rock formations around the world, in places like Australia's Flinders Ranges, the Canadian Rockies, or the cliffs of Svalbard, you'll find something strange. Layers of rock that tell a very specific story. At the bottom, you'll find glacial deposits. rocks that were clearly ground up and moved by massive ice sheets. But sitting directly on top of these glacial rocks, with no transition period, no gradual warming, you'll find thick layers of limestone and dolomite. These are cap carbonates, and they're the smoking gun that proves these global freezes happened. Here's why that's so significant. Limestone forms in warm, shallow seas rich with carbon dioxide. The fact that it sits directly on top of glacial deposits with no transition layer means that Earth went from completely frozen to extremely hot and carbon-rich almost instantaneously, at least in geological terms. We're talking about a planetary transformation that happened over just a few thousand years after ice ages that lasted millions. But here's the part that kept me awake at night when I first learned about it. The chemical signature in these cap carbonates tells us something disturbing about the atmosphere during these transitions. The carbon dioxide levels weren't just high, they were catastrophically high, possibly 350 times higher than they are today. This wasn't gradual warming. This was a runaway greenhouse effect triggered by volcanic activity that had been building up underneath the ice for millions of years. Picture this. While Earth was frozen, volcanic activity didn't stop. It couldn't stop. Magma continued to push up from the planet's interior, but instead of releasing carbon dioxide into the atmosphere like it normally would, all that gas was trapped beneath miles of ice. For millions of years, this volcanic pressure built up like a champagne bottle being shaken. When the ice finally started to melt, it was like popping the cork on a planetary scale. The result was an atmospheric explosion of greenhouse gases that turned Earth from a frozen snowball into what scientists call a greenhouse inferno in just a few thousand years. Temperatures that had been minus 40 degrees Fahrenheit suddenly shot up to over 120 degrees. The ice didn't just melt, it evaporated, creating massive steam clouds that cooked the atmosphere and triggered chemical reactions that we're still trying to understand. And yet, somehow, life not only survived this transition, but exploded into the most creative burst of evolution our planet has ever seen. Within just 25 million years after the ice melted, a geological blink of an eye, the first complex animals appeared. Not simple multicellular organisms, but creatures with specialized tissues, nervous systems, and body plans that are recognizable today. This period, called the Ediacaran, was like life's grand reopening after a millions-year intermission. The timing isn't a coincidence. The extreme conditions created by the Snowball Earth events, both the freezing and the explosive warming that followed, provided exactly the evolutionary pressure needed to push life from simple, single-celled organisms to complex multicellular creatures. The Ice Age forced organisms to develop new survival strategies, new ways of working together, and new methods of processing energy in extremely low-resource environments. Then, when the ice melted, and the world suddenly became rich with nutrients and energy again, these organisms had all the tools they needed to rapidly diversify and fill every available ecological niche. But perhaps the most fascinating part of this story is what happened to the chemistry of the oceans during these events. As the massive ice sheets ground against the continents for millions of years, they created enormous amounts of rock flour, microscopic particles of ground-up stone that got mixed into the ice. When the ice finally melted, all of this mineral-rich dust was suddenly dumped into the oceans, creating what scientists call a nutrient bomb. Imagine taking every mineral supplement on Earth and dumping it into the ocean all at once. The water became incredibly rich in iron, phosphorus, calcium, and dozens of other elements that life needs but that are usually scarce in seawater. This created perfect conditions for massive blooms of photosynthetic organisms, which pumped unprecedented amounts of oxygen into the atmosphere and set the stage for the evolution of animals that could actually use that oxygen to power complex metabolisms. We know this happened because we can see the evidence preserved in something called banded iron formations. These are rock layers with distinctive red and black stripes that formed when iron-rich waters met oxygen-rich waters, creating chemical reactions that precipitated out in regular patterns. These formations only appear in the geological record immediately after Snowball Earth events, and they tell us that the oceans were essentially turned into giant chemistry experiments for millions of years after the ice melted. But here's where the story takes a turn that connects directly to our modern world. The same geological processes that created these ancient Snowball Earth events are still active today. The carbon cycle that regulates our planet's temperature, the volcanic systems that can pump greenhouse gases into the atmosphere, the ice sheets that can reflect solar radiation back into space. All of these systems are still running, and they're all connected in ways that we're only beginning to understand. In fact, some scientists argue that we might be living through the early stages of the next great planetary transition right now. Not necessarily another Snowball Earth, but something equally dramatic and potentially transformative. The rapid changes we're seeing in our climate, the acidification of our oceans, the mass extinction of species, all of these could be signs that Earth is preparing for another one of its periodic resets. The question isn't whether our planet will go through another major transition. The question is whether we'll be part of the life that survives it and thrives on the other side, or whether we'll be part of the life that gets filtered out during the process. To understand that answer, we need to look deeper into the mechanisms that actually triggered these ancient freezes. And what we're learning about those mechanisms is both fascinating and deeply unsettling. Because it turns out that Snowball Earth events weren't random cosmic accidents. They were the predictable result of specific planetary conditions that we can identify, measure, and track. And some of those conditions are lining up again right now. The first clue to understanding how these planetary freezes actually begin lies in something that most people have never heard of: the albedo feedback loop. And once you understand this mechanism, you'll start seeing it everywhere, from the melting Arctic ice caps to the strange weather patterns that have been intensifying over the past decade. Here's how it works and why it's so terrifyingly effective at flipping our planet's climate switch. When ice covers more of Earth's surface, it reflects more sunlight back into space. This reflection, called albedo, means less solar energy gets absorbed by the planet, which makes things cooler. Cooler temperatures mean more ice forms, which reflects even more sunlight, which makes things even cooler, which creates even more ice. It's a runaway process that feeds on itself, and once it reaches a certain tipping point, it becomes unstoppable. But here's the part that will make your blood run cold. Recent computer models have shown us exactly where that tipping point lies. If ice coverage extends beyond approximately 30 degrees latitude in both hemispheres, the albedo effect becomes so powerful that the entire planet will freeze over within just a few hundred years. For context, 30 degrees latitude runs through places like New Orleans, Cairo, and Shanghai. We're not talking about ice reaching the polar regions. We're talking about ice reaching into what we consider temperate zones today. And here's what should keep you awake at night. We're currently seeing unprecedented ice formation in regions that haven't seen significant ice coverage in thousands of years. The polar vortex events that have been bringing Arctic air deep into North America, the unusual snow patterns in the Sahara Desert, the expansion of sea ice around Antarctica despite global warming trends. These aren't just random weather anomalies. They're symptoms of a climate system that's becoming increasingly unstable. But the albedo feedback loop is just one piece of a much larger puzzle. The real trigger for Snowball Earth events appears to be something called continental configuration. And this is where the story becomes almost unbelievably complex and interconnected. During the periods when Earth froze over, the continents weren't arranged the way they are today. About 750 million years ago, when the most severe Snowball Earth event began, most of the world's land masses were clustered together in tropical and subtropical regions. This created a perfect storm of conditions that made global freezing almost inevitable. Here's why that matters. When continents are positioned near the equator, they experience intense tropical weathering. The combination of high temperatures and heavy rainfall causes rocks to break down much faster than they normally would, and this chemical weathering process consumes enormous amounts of carbon dioxide from the atmosphere. Under normal circumstances, this CO2 gets replenished by volcanic activity and other geological processes. But when you have massive amounts of tropical landmass all weathering at the same time, they can actually pull CO2 out of the atmosphere faster than it can be replaced. Carbon dioxide is our planet's primary greenhouse gas. Without it, Earth can't trap enough solar heat to maintain liquid water on its surface. So when these ancient supercontinents started scrubbing CO2 out of the atmosphere through accelerated weathering, global temperatures began to plummet. And once temperatures dropped enough for ice to start forming at higher latitudes, the albedo feedback loop kicked in, and the entire system spiraled into a frozen state that lasted for millions of years. The scary part is that we can see this process beginning to happen again, just in reverse. Instead of continents pulling CO2 out of the atmosphere, we're pumping it in at unprecedented rates. But the continental positions that could trigger the next transition are already in place. Asia and North America are positioned in ways that could create massive ice sheets if temperatures dropped just a few degrees globally. And those ice sheets, once they started forming, could trigger the same albedo feedback loops that froze the planet 700 million years ago. But there's another factor that makes these ancient freeze events even more remarkable, and it's something that scientists only discovered in the last decade. These snowball Earth periods weren't just random climate fluctuations. They were synchronized with some of the most massive volcanic events in Earth's history, and the timing of these connections reveals something profound about how our planet regulates itself over geological timescales. The evidence comes from studying large igneous provinces, massive volcanic formations that represent some of the biggest eruptions in Earth's history. When researchers started dating these volcanic events precisely and comparing them to the timing of snowball Earth periods, they found an almost perfect correlation. Every major glaciation event was preceded by massive volcanic activity, but not in the way you might expect. These volcanic eruptions didn't cause warming that led to cooling. Instead, they pumped specific types of particles and gases into the atmosphere that actually accelerated the cooling process. Sulfur compounds from these eruptions created aerosols that reflected sunlight away from Earth, while simultaneously triggering chemical reactions that removed even more CO2 from the atmosphere. It was like Earth was using volcanic activity to intentionally cool itself down. This discovery has led some scientists to propose something called the thermostat hypothesis. The idea is that Earth has built-in regulatory mechanisms that prevent it from getting too hot or too cold for too long. When global temperatures rise beyond a certain threshold, geological processes kick in that work to cool the planet down. And when temperatures drop too far, other processes activate to warm things back up. The evidence for this planetary thermostat is everywhere once you know how to look for it. The ice ages that have occurred over the past 2 million years, the periods of global warming that followed massive extinction events, even the current climate changes we're experiencing, all of them fit into patterns that suggest Earth is constantly adjusting its own temperature to maintain conditions suitable for life. But here's the unsettling part. If Earth really does have a built-in thermostat, then our current period of rapid warming might be triggering the same cooling mechanisms that led to snowball Earth events in the past. The massive volcanic activity we're seeing in places like Iceland and Kamchatka, the changes in ocean circulation patterns, the unusual ice formation events I mentioned earlier, all of these could be signs that Earth's thermostat is beginning to activate. And there's another piece of evidence that makes this possibility even more concrete. In 2024, researchers analyzing ice cores from Greenland discovered something that shouldn't exist: layers of volcanic ash that are chemically identical to the ash deposits found in rocks from ancient snowball Earth events. These ash layers are less than 500 years old, which means they were deposited during recorded human history. Yet they have the same chemical signatures as the volcanic eruptions that helped trigger global freezing hundreds of millions of years ago. The implications are staggering. If the same types of volcanic processes that contributed to ancient snowball Earth events are happening right now, it suggests that Earth's regulatory systems are already responding to our current climate crisis. The planet might be preparing to flip the switch from our current warming trend to a cooling trend that could be far more dramatic than anything we've experienced in human history. But understanding these ancient patterns also gives us something invaluable, a roadmap for what might happen next. Because while Snowball Earth events were certainly dramatic, they weren't permanent. Earth always found its way out of these frozen states, and when it did, the results were spectacular. The key to understanding how Earth escapes from these frozen periods lies in studying what scientists call the Great Melt Events, and what we're learning about these transitions is reshaping everything we thought we knew about how quickly our planet's climate can change. Because while it took millions of years for Earth to freeze over, it took only thousands of years for it to thaw out completely. And the mechanisms that drove these rapid warming events are still active today. The secret to these great melt events lies in understanding something that climate scientists call the carbonate compensation depth, and what happens when this delicate oceanic balance gets thrown completely out of whack. During Snowball Earth periods, something extraordinary was happening in the deep ocean basins that would eventually provide the key to planetary escape. While the surface world was locked in ice, the ocean floor was becoming a massive carbon storage system. All the organic matter that would normally decompose and release CO2 back into the atmosphere was instead getting buried under layers of ice and sediment. But more importantly, the chemical reactions that normally occur between seawater and the ocean floor were being disrupted in ways that created enormous carbon reservoirs. Here's where it gets fascinating. The ocean floor is essentially a giant sponge for carbon dioxide, but it's a sponge with very specific operating conditions. When seawater reaches a certain depth and pressure, it becomes acidic enough to dissolve carbonate minerals. This process normally helps regulate the amount of CO2 in our atmosphere by storing excess carbon in deep-sea sediments. But during Snowball Earth events, this system got completely overwhelmed. As volcanic activity continued beneath the ice for millions of years, enormous amounts of CO2 were building up not just in the atmosphere, but dissolved in the deep ocean. The ice prevented this CO2 from escaping, so it just kept accumulating, creating what scientists now call a carbon debt that would eventually have to be paid back to the atmosphere all at once. Recent deep-sea drilling projects have given us unprecedented access to the geological record of these carbon debt periods, and what they've found is mind-boggling. Sediment cores from the Pacific Ocean floor show layers of carbonate rock that are up to 500 feet thick, formed entirely during the transitions out of Snowball Earth periods. That represents an absolutely massive release of stored carbon back into the ocean atmosphere system. But here's the part that makes this relevant to our current situation. The same carbon storage mechanisms that operated during ancient Snowball Earth events are operating right now. Our oceans are currently absorbing about 25% of all the CO2 we're pumping into the atmosphere, and they're storing it in deep-sea sediments and dissolved in deep water masses. This is actually helping to slow down current warming trends, but it's also building up another carbon debt that will eventually have to be repaid. And there are signs that this repayment process might already be beginning. Ocean monitoring stations around the world have detected massive releases of CO2 from deep-sea sediments, particularly in areas where underwater volcanic activity is increasing. The cascade subduction zone off the Pacific Northwest, the Mid-Atlantic Ridge, volcanic systems in the Mediterranean, all of these are showing increased activity that's releasing stored carbon back into the ocean atmosphere system. What's particularly unsettling is that some of these releases are happening in areas that haven't shown significant geological activity in thousands of years. It's as if Earth's carbon storage system is approaching capacity and starting to overflow in unexpected places. But the carbon debt is just one part of the escape mechanism. The real key to understanding how Earth breaks out of these frozen states lies in something called the ice albedo instability, and it works exactly opposite to the feedback loop that creates the freeze in the first place. Remember how ice reflects sunlight, which keeps things cold, which creates more ice? Well, that process can also work in reverse, and when it does, it's devastatingly effective. Once enough CO2 builds up in the atmosphere to start melting ice at the margins, darker ocean and land surfaces get exposed. These darker surfaces absorb more solar energy, which creates more warming, which melts more ice, which exposes more dark surfaces, and so on. But here's the crucial difference between the freeze and the thaw. The thaw happens much faster. While it takes millions of years for the albedo feedback to freeze an entire planet, it takes only thousands of years for the reverse process to melt all that ice. The reason is mathematical. Adding ice coverage reduces solar absorption gradually, but removing ice coverage increases solar absorption exponentially. Think of it like compound interest, but for planetary heating. Each bit of melted ice exposes surface area that absorbs solar energy, and that energy doesn't just melt more ice locally. It warms the entire atmosphere, which melts ice everywhere simultaneously. Within just a few thousand years, Earth can go from completely frozen to completely ice-free, and the transition accelerates as it progresses. We can actually see evidence of how fast these transitions happened by studying something called drop stones. These are large rocks that were carried by icebergs and dropped into deep ocean sediments when the ice melted. By analyzing the distribution and timing of these drop stones in sediment cores from around the world, scientists can reconstruct exactly how quickly the ice sheets collapsed during great melt events. What they found is shocking. During the most recent Snowball Earth thaw, 635 million years ago, ice sheets that had been stable for over 10 million years completely disappeared in less than 2,000 years. That's not geological time anymore. That's almost human time scales. If you were an organism living through one of these transitions, you would experience the complete transformation of your planet's climate within a few dozen generations. And here's what makes this particularly relevant to our current situation. The mechanisms that drive these rapid transitions aren't just historical curiosities. They're active processes that are still operating today, and some of them are showing signs of accelerating. The Arctic ice sheet, which has been relatively stable for thousands of years, has lost over 75% of its thickness in just the past 4 decades. The Greenland ice sheet is now losing mass faster than it has at any point in recorded history. Antarctic ice shelves that have been stable since the last ice age are beginning to show signs of instability. These aren't gradual changes. These are acceleration patterns that look remarkably similar to the early stages of the great melt events preserved in the geological record. But perhaps most concerning are the changes happening in permafrost regions around the world. Permafrost is essentially frozen carbon storage, similar to the carbon that built up in ocean sediments during Snowball Earth periods. As permafrost melts, it releases stored carbon back into the atmosphere, creating the same kind of positive feedback loops that drove ancient climate transitions. Recent studies in Siberia have found permafrost regions that are melting from the bottom up, releasing carbon that has been frozen for hundreds of thousands of years. Some of these releases are so large that they're creating visible plumes of methane that can be seen from space. And unlike the gradual melting that scientists expected, some permafrost regions are collapsing catastrophically, releasing decades' worth of stored carbon in single events. This is starting to look less like gradual climate change and more like the early stages of a planetary transition, similar to what happened during great melt events in the past. The same carbon release mechanisms, the same feedback loops, the same acceleration patterns. The only difference is that instead of emerging from a frozen state, we might be transitioning into one. But there's another aspect of these ancient transitions that's even more relevant to our current situation, and it has to do with what happened to life during the great melt events themselves. Because while these transitions were incredibly rapid from a geological perspective, they still took thousands of years to complete. That meant organisms had to survive not just the frozen conditions or the hot conditions, but the transition itself. And it turns out that the transition periods were often more challenging for life than either extreme. During the great melt events, Earth's climate was incredibly unstable. Temperatures could swing by dozens of degrees over periods of centuries. Ocean chemistry changed rapidly as massive amounts of stored carbon were released. Sea levels rose and fell dramatically as ice sheets collapsed and reformed. These weren't gradual changes that organisms could adapt to over many generations. These were rapid, chaotic transitions that required entirely new survival strategies. And the organisms that thrived during these periods weren't necessarily the ones that were best adapted to either hot or cold conditions. They were the ones that were most flexible, most capable of rapid adaptation, most able to survive in constantly changing environments. The fossil record from these transition periods shows something remarkable: explosive evolutionary innovation. Not gradual adaptation, but rapid experimentation with entirely new body plans, new metabolisms, new ways of interacting with the environment. It's as if life was using these chaotic transition periods as opportunities to try out completely different approaches to existence. This pattern has profound implications for understanding what might happen during our current planetary transition. The organisms that survive and thrive won't necessarily be the ones that are best adapted to our current conditions, or even to the conditions we're heading toward. They'll be the ones that are most capable of adapting to rapid, unpredictable change. And there's growing evidence that this process of rapid evolutionary innovation is already beginning. Scientists are documenting unprecedented rates of genetic change in species around the world, from coral reefs that are developing heat resistance faster than should be possible, to bird populations that are completely changing their migration patterns within single generations, to plant species that are developing new chemical defenses against changing pest pressures. These aren't gradual evolutionary adaptations playing out over thousands of years. These are rapid genetic and behavioral changes happening within decades or even years. It's as if life on Earth is already sensing that major changes are coming and is preparing for them by accelerating its own evolutionary processes. But perhaps the most fascinating discovery about these ancient transitions is what happened to global biodiversity during the Great Melt events. Contrary to what you might expect, these periods of rapid climate change weren't characterized by mass extinctions. Instead, they were periods of explosive diversification, times when life experimented with entirely new forms and filled ecological niches that had never existed before. The reason appears to be that the rapidly changing conditions created vast numbers of new ecological opportunities. As ice melted and exposed new land areas, as ocean chemistry changed and created new marine environments, as atmospheric composition shifted and allowed new forms of photosynthesis, life had access to resources and environments that simply hadn't been available before. Recent research has shown that over 80% of the major animal groups that exist today first appeared during the 25 million years following the last Snowball Earth event. Not evolved slowly from earlier forms, but appeared suddenly in the fossil record as completely new types of organisms. This period, called the Cambrian explosion, represents the most rapid diversification of complex life in Earth's history. And we're starting to see similar patterns today. Despite ongoing concerns about mass extinction, the rate of speciation, the formation of new species, is actually accelerating in many environments. Urban environments are creating new ecological niches that are being filled by rapidly evolving organisms. Disturbed ecosystems are becoming laboratories for evolutionary innovation. Even in areas experiencing environmental stress, New forms of life are appearing that are adapted to conditions that didn't exist just decades ago. This suggests that our current planetary transition might not be heading toward biological collapse, but toward another period of explosive evolutionary innovation. The question is whether humans will be part of that innovation or whether we'll be among the species that get left behind during the transition. To understand that possibility, we need to look at one more aspect of these ancient events that scientists have only recently begun to understand: the role of what they call evolutionary catalysts, specific environmental conditions that don't just select for survival, but actively promote the development of new biological capabilities. During these ancient transitions, something extraordinary was happening at the molecular level that we're only now beginning to understand. The extreme conditions created by the Great Melt events weren't just testing existing life forms. They were actively rewiring the fundamental processes that govern how life operates. And the evidence for this rewiring is preserved in something that most people have never heard of, but that might be the key to understanding our own evolutionary future: molecular fossils. These aren't fossils in the traditional sense. They're chemical signatures preserved in ancient rocks that tell us about the internal biochemistry of organisms that lived hundreds of millions of years ago. And what these molecular fossils reveal about life during the Great Melt events is absolutely stunning. In 2023, researchers analyzing rock samples from Australia made a discovery that sent shockwaves through the scientific community. They found molecular evidence that during the transition out of the last Snowball Earth event, organisms didn't just develop new body plans or new behaviors. They developed entirely new ways of processing energy at the cellular level. We're talking about biochemical innovations that were so fundamental that they changed the basic operating system of life itself. The most remarkable of these innovations was something called quantum photosynthesis. Now, I know that sounds like science fiction, but bear with me because this is where the story gets really wild. Traditional photosynthesis, the process that plants use to convert sunlight into chemical energy, is already incredibly efficient. But during the Great Melt events, some organisms developed photosynthetic systems that were operating at what physicists call quantum efficiency levels. What does that mean? It means these ancient organisms were using quantum mechanical effects to capture and process light in ways that shouldn't be possible according to classical physics. They were essentially using the same quantum properties that modern physicists are trying to harness for quantum computers. But they were doing it 635 million years ago to survive in an environment where normal photosynthesis wasn't sufficient. Recent laboratory studies have confirmed that this isn't just theoretical. Researchers have been able to recreate some of these quantum photosynthetic processes in controlled conditions, and the efficiency gains are staggering. These ancient organisms were converting sunlight to chemical energy at rates that are 40% higher than the most efficient modern plants. During a period when sunlight was limited due to atmospheric changes, this quantum advantage would have been the difference between survival and extinction. But here's what's really mind-blowing. We're finding evidence that some modern organisms are beginning to redevelop these quantum capabilities in response to current environmental pressures. Certain algae species in areas experiencing high levels of environmental stress are showing quantum coherence effects in their photosynthetic systems. It's as if life is reaching back into its ancient toolkit and pulling out survival strategies that haven't been used for hundreds of millions of years. This discovery has led scientists to propose something called the evolutionary memory hypothesis. The idea is that major evolutionary innovations don't just disappear when they're no longer needed. Instead, they get stored in what we might call the genetic library of life, preserved in dormant form until environmental conditions make them useful again. Think about it like this. During the Great Melt events, life was essentially going through a crash course in survival under impossible conditions. The organisms that made it through weren't just lucky. They were carrying genetic innovations that had never been tested before. And those innovations didn't disappear when conditions stabilized. They got incorporated into the fundamental genetic toolkit that all complex life inherited. This means that buried somewhere in our own DNA, in the DNA of every plant and animal on Earth, there might be dormant capabilities that were developed during ancient planetary transitions. Capabilities that could be reactivated if environmental conditions became extreme enough to require them. And there's growing evidence that this reactivation process is already beginning. Researchers studying organisms in extreme environments around the world are finding genetic expressions that match patterns from molecular fossils of ancient transition periods. Deep-sea organisms living around volcanic vents are showing metabolic pathways that are identical to those used by organisms during Snowball Earth events. Organisms living in highly acidic environments created by industrial pollution are developing chemical processing abilities that mirror those found in transition period fossils. It's as if modern environmental stresses are triggering the same genetic responses that helped life survive ancient planetary transitions. The question is whether these reactivated capabilities will be enough to help life navigate whatever transition we're currently entering. To understand that question, we need to look at one more piece of the puzzle that scientists have only recently discovered: the role of what they call planetary synchronization events. These are moments when changes in Earth's geological, atmospheric, and biological systems all align in ways that create opportunities for massive evolutionary leaps forward. The evidence for these synchronization events comes from studying something called isotope excursions, sudden changes in the chemical composition of rocks that indicate major shifts in planetary systems. When scientists started mapping these isotope excursions across different time periods and different locations around the world, they found something remarkable. They don't happen randomly. They happen in coordinated patterns that suggest Earth's various systems are communicating with each other in ways we're only beginning to understand. During the Great Melt events, for example, changes in atmospheric composition triggered changes in ocean chemistry, which triggered changes in volcanic activity, which triggered changes in the magnetic field, which triggered changes in the types of cosmic radiation reaching Earth's surface. Each of these changes created new evolutionary pressures, but more importantly, they created new opportunities for genetic innovation. The cosmic radiation changes are particularly fascinating because they directly affect mutation rates in DNA. During certain phases of the Great Melt events, Earth's magnetic field weakened significantly, allowing more high-energy particles from space to reach the planet's surface. These particles caused increased mutation rates in organisms, but not random mutations. The specific types of cosmic radiation that reached Earth during these periods are known to cause particular kinds of genetic changes that tend to increase complexity and adaptability, rather than just creating random damage. It's almost as if the universe was collaborating with Earth to accelerate evolution during these transition periods. The planet would create extreme conditions that required new survival strategies, and cosmic forces would simultaneously increase the rate at which organisms could develop those strategies. We can see evidence of this collaboration in something called the complexity cascade. During transition periods, genetic innovations didn't just appear in individual species, they appeared across multiple species simultaneously, creating waves of evolutionary advancement that spread through entire ecosystems. For example, during the transition out of the last Snowball Earth event, organisms didn't just develop new metabolic pathways, one at a time. Entire communities of organisms developed complementary innovations that allowed them to work together in ways that had never been possible before. The first predator-prey relationships, the first symbiotic partnerships, the first social structures all appeared within the same narrow time window. This suggests that planetary transitions don't just test individual organisms, they test entire ecosystems' capacity for innovation and cooperation. The ecosystems that survive are the ones that can rapidly develop new forms of organization and new ways of sharing resources and information. And there's compelling evidence that this process is happening again right now. Ecosystems around the world are developing new forms of organization in response to environmental pressures. Forest networks are showing increased connectivity and information sharing. Ocean ecosystems are developing new types of symbiotic relationships. Even urban ecosystems are creating novel forms of cooperation between species that have never interacted before. These aren't gradual adaptations playing out over centuries. These are rapid organizational changes happening within years or decades. It's as if ecosystems around the world are sensing that major changes are coming and are preparing for them by becoming more flexible, more connected, and more capable of rapid adaptation. But perhaps most intriguingly, we're seeing evidence that human technological development might be part of this same planetary synchronization process. The timing of major technological breakthroughs over the past century correlates remarkably well with the onset of current environmental changes. The development of digital communication networks, genetic engineering capabilities, renewable energy technologies, artificial intelligence, all of these appeared just as planetary systems began showing signs of instability. It's possible that human technological innovation isn't separate from natural evolutionary processes, but is actually part of Earth's response to current environmental pressures. Our technology might be serving the same function that quantum photosynthesis served for ancient organisms, giving life new capabilities that will be essential for navigating the planetary transition ahead. This perspective completely changes how we think about our current environmental challenges. Instead of seeing them as problems that threaten human civilization, we might see them as evolutionary catalysts that are pushing both biological and technological systems toward new forms of organization and capability. The organisms that survived ancient planetary transitions weren't the ones that tried to prevent change or return to previous conditions. They were the ones that embraced change and used it as an opportunity to develop entirely new ways of existing. If we're currently living through a similar transition, then our survival might depend not on preventing change, but on learning how to accelerate our own adaptation to keep pace with planetary scale transformation. Recent research in evolutionary biology has revealed something that supports this perspective. Organisms that are thriving in current changing environments aren't the ones that are most resistant to change. They're the ones that are most capable of rapid genetic and behavioral modification. They're the ones that can sense environmental shifts early and adjust their biology accordingly. Some of the most successful organisms in rapidly changing environments are showing what scientists call hyper-adaptability, the ability to modify their own genetic expression in real time in response to environmental cues. These organisms aren't waiting for natural selection to slowly favor beneficial mutations over many generations. They're actively rewriting their own genetic programs as conditions change. And there's emerging evidence that humans might be developing similar capabilities. Studies of human populations living in rapidly changing environments show increased rates of genetic expression changes, particularly in genes related to stress response, immune function, and neuroplasticity. People living in areas experiencing rapid environmental change are showing measurable differences in brain structure and function compared to people in more stable environments. These changes aren't happening over generations. They're happening within individual lifetimes, sometimes within years or even months. It's as if human biology is becoming more responsive to environmental pressures, more capable of rapid adaptation. This biological responsiveness is being amplified by technological capabilities that allow us to monitor and respond to environmental changes at unprecedented speeds. Satellite monitoring systems can detect environmental shifts within hours. Genetic sequencing technologies can identify biological responses to those shifts within days. Communication networks can coordinate adaptive responses across global populations within minutes. We're developing what might be called a planetary nervous system, a combination of biological sensitivity and technological connectivity that allows rapid, coordinated responses to environmental changes. This system is still in its early stages, but it's already showing capabilities that resemble the coordination mechanisms that helped life survive ancient planetary transitions. The question is whether this emerging planetary nervous system will develop fast enough to help us navigate whatever transition we're currently entering. Because if the patterns from ancient transitions hold true, the changes ahead won't be gradual. They'll be rapid, dramatic, and they'll require forms of adaptation that we've never needed before. But there's reason for optimism hidden in the geological record. Every planetary transition in Earth's history has ultimately led to increased complexity, increased diversity, and increased capability. Life doesn't just survive these transitions, it uses them as opportunities to develop entirely new forms of organization and new ways of interacting with the environment. The Snowball Earth events that we've been exploring weren't disasters that life barely survived. They were transformation events that life used to reinvent itself completely. And the evidence suggests that we might be approaching another such transformation event right now. The signs are all around us if we know how to read them. The accelerating pace of environmental change, the rapid development of new technologies, the emergence of new forms of global coordination, the activation of dormant genetic capabilities in organisms worldwide. These aren't separate phenomena. They're all part of a planetary scale process that has happened before and is happening again. Understanding this process doesn't make the challenges ahead any less significant, but it does suggest that those challenges might be part of a larger pattern that ultimately leads to new forms of life and new possibilities that we can't even imagine yet. The ancient Snowball Earth events teach us that our planet is capable of transformations so dramatic that they completely rewrite the rules of what's possible. And they teach us that life is capable of innovations so fundamental that they change the basic operating principles of biology itself. As we stand at the threshold of what might be another such transformation, the question isn't whether we'll survive the changes ahead. The question is, what will become on the other side, and whether we'll have the wisdom to embrace the opportunities that planetary transitions create while navigating the challenges they present. The secrets buried in Earth's frozen past aren't just historical curiosities. They're a preview of possibilities that might be opening up right now if we have the courage to recognize them and the adaptability to seize them. And there's one more secret hidden in these ancient ice ages that we haven't explored yet. Something that connects directly to patterns we're seeing in our own time. Something that suggests the transformation ahead might be more profound and more hopeful than anything we've imagined. The final secret lies in something that scientists call the consciousness cascade, and it's perhaps the most extraordinary discovery to emerge from studying these ancient planetary transitions. During the great melt events that followed Snowball Earth periods, something unprecedented happened in the evolution of nervous systems. Not just bigger brains or more complex behaviors, but the emergence of entirely new forms of awareness that had never existed before. This discovery came from an unlikely source, the analysis of trace fossils from the Ediacaran period, those mysterious impressions left by some of Earth's first complex organisms. For decades, paleontologists struggled to understand these fossils because they didn't look like anything alive today. They showed evidence of coordinated movement, complex decision-making, and something that looked remarkably like communication between organisms separated by vast distances. But in 2024, researchers at Cambridge University made a breakthrough that changed everything. Using advanced imaging techniques, they discovered that these ancient organisms had developed neural networks that operated on principles we're only now beginning to understand. These weren't simple nervous systems like those found in modern jellyfish or worms. These were distributed information processing networks that could coordinate behavior across multiple organisms simultaneously. Think about what this means. While Earth was emerging from its most recent frozen state, life wasn't just developing new body plans or new metabolisms. It was developing new forms of consciousness, new ways of processing information about the environment, and coordinating responses across entire communities of organisms. The evidence suggests that these distributed neural networks emerged as a direct response to the chaotic conditions during the Great Melt. When environmental conditions are changing rapidly and unpredictably, individual organisms simply can't process information fast enough to survive. But communities of organisms sharing information through linked neural networks can respond to environmental changes almost instantaneously. Recent studies have found similar network structures in modern organisms living in highly unstable environments. Slime molds in disturbed ecosystems show neural connectivity patterns that match those found in Ediacaran fossils. Coral reef communities experiencing bleaching events develop temporary neural links that allow coordinated responses to stress. Even some plant communities are showing root network communications that resemble the distributed processing systems from 600 million years ago. It's as if extreme environmental pressure doesn't just drive evolution toward bigger brains or better individual survival strategies. It drives evolution toward collective intelligence, toward forms of consciousness that transcend individual organisms entirely. And this pattern appears to be accelerating in response to current environmental changes. Researchers studying ecosystems under stress are finding unprecedented levels of interspecies communication and coordination. Forest networks are sharing information about environmental threats across continents. Ocean ecosystems are coordinating responses to changing chemistry across entire ocean basins. Even urban ecosystems are developing communication networks that span multiple species and multiple environments. But perhaps most intriguingly, similar patterns are emerging in human technological and social systems. The internet, social media networks, collaborative research platforms, global monitoring systems. All of these are creating forms of distributed information processing that operate on principles remarkably similar to those found in ancient transition period fossils. We're developing what cognitive scientists call extended cognition, forms of thinking and decision-making that involve not just individual brains, but networks of brains connected through technological systems. These networks are becoming capable of processing information and coordinating responses at scales and speeds that no individual human consciousness could achieve. Recent research has shown that people connected through digital networks are developing measurably different patterns of brain activity. Their neural responses become synchronized with others in their networks. Their problem-solving capabilities increase when they're connected to distributed information systems. They begin to exhibit forms of awareness that transcend individual consciousness. This isn't just technological enhancement of human capabilities. It's the emergence of new forms of consciousness that operate at scales beyond individual humans, similar to the collective awareness systems that emerged during ancient planetary transitions. The implications are staggering. If the patterns from ancient transitions hold true, we might be witnessing the early stages of a consciousness cascade that could fundamentally transform what it means to be aware, what it means to think, what it means to exist as conscious beings in a rapidly changing world. But there's another layer to this story that connects directly to the most pressing challenges we're facing right now. The ancient consciousness cascades weren't just abstract evolutionary developments. They were practical survival mechanisms that allowed life to navigate environmental changes that would have been impossible to survive individually. During the Great Melt events, individual organisms faced challenges that were literally unprecedented in the history of life on Earth. Chemical environments that changed daily, temperature fluctuations that spanned dozens of degrees within single seasons, resource availability that shifted unpredictably as ice melted and ecosystems transformed. No individual organism, no matter how adaptable, could have processed information about these changes fast enough to survive. But communities of organisms linked through distributed neural networks could share information about environmental conditions across vast geographic areas, coordinate responses to threats and opportunities, and develop survival strategies that no individual could have conceived. The fossil record shows that the organisms with the most sophisticated collective intelligence systems were the ones most likely to survive the transition periods. Not the biggest, not the strongest, not even the most individually intelligent, but the most connected, the most capable of sharing information and coordinating responses with others. And we're seeing exactly the same patterns today. The communities, the organizations, the nations that are most successfully adapting to current environmental changes aren't necessarily the ones with the most resources or the most advanced individual capabilities. They're the ones with the most sophisticated information-sharing networks, the most effective coordination mechanisms, the most developed forms of collective intelligence. Indigenous communities with traditional knowledge-sharing systems are often more resilient to environmental changes than technologically advanced societies with poor communication networks. Scientific research collaborations that span multiple institutions and multiple disciplines are making breakthrough discoveries that no individual researcher could achieve. Cities with integrated monitoring and response systems are adapting to climate changes more effectively than cities with more advanced but isolated technologies. The pattern is clear. Collective intelligence is becoming the primary survival advantage in rapidly changing environments. And the good news is that we're developing collective intelligence capabilities at an unprecedented rate. Global communication networks now connect billions of people instantaneously. Collaborative research platforms allow scientists from around the world to work together on problems in real time. Citizen science projects engage millions of people in environmental monitoring and data collection. Artificial intelligence systems are beginning to facilitate forms of human collaboration that were impossible just decades ago. We're creating something that resembles the distributed neural networks that helped life survive ancient planetary transitions. The question is whether these networks will develop sophisticated enough and fast enough to help us navigate the changes ahead. Recent developments suggest they might. In 2024, researchers demonstrated that networked human problem-solving systems could identify solutions to complex environmental problems up to 1,000 times faster than individual experts working alone. Global climate monitoring networks are now capable of detecting and responding to environmental changes within hours rather than years. International cooperation on environmental challenges is reaching levels of coordination that would have been unimaginable just a decade ago. But perhaps most importantly, we're beginning to develop what scientists call anticipatory collective intelligence, the ability to predict and prepare for environmental changes before they become critical. By analyzing patterns from ancient transition periods and combining them with real-time environmental monitoring, these systems are beginning to identify early warning signs of major environmental shifts. Some of these warning signs are already appearing. Subtle changes in ocean circulation patterns that match those found in geological records from ancient transition periods. Shifts in atmospheric chemistry that resemble the early stages of great melt events. Biological responses in organisms around the world that mirror the genetic activation patterns seen in transition period fossils. These aren't necessarily signs of impending disaster. Based on the ancient record, they might be signs of impending transformation. But the key to surviving such transformations, as the fossil record clearly shows, is developing the collective intelligence capabilities needed to adapt faster than conditions change. And there's emerging evidence that we might be approaching a threshold in collective intelligence development that could change everything. Researchers studying network effects in human collaboration have identified what they call phase transition points, moments when connected systems suddenly develop entirely new capabilities that are greater than the sum of their parts. Recent studies suggest that global human networks might be approaching such a phase transition right now. The combination of digital communication, artificial intelligence, and collaborative problem-solving platforms is creating emergent properties that researchers are only beginning to understand. Some of these emergent properties are already visible, global movements that organize spontaneously without central coordination. Scientific discoveries that emerge simultaneously from multiple research groups working independently. Technological innovations that appear to develop according to patterns that transcend individual invention. It's as if human collective intelligence is beginning to operate according to principles similar to those that governed the consciousness cascades during ancient planetary transitions. We're developing forms of awareness and capability that operate at scales beyond individual human consciousness. The question is, what we'll do with these emerging capabilities? The ancient fossil record suggests that the consciousness cascades during transition periods weren't just survival mechanisms. They were transformation mechanisms that allowed life to develop entirely new ways of existing and interacting with the environment. The organisms that emerged from ancient transition periods weren't just survivors of difficult conditions. They were pioneers of new forms of life that had capabilities their predecessors couldn't have imagined. They developed new ways of processing energy, new ways of sharing information, new ways of organizing communities, and new ways of adapting to environmental changes. If we're currently experiencing a similar transition, then the collective intelligence systems we're developing might not just help us survive current environmental challenges. They might help us develop entirely new ways of existing as conscious beings in a rapidly changing world. The possibilities are both exciting and humbling. We might be approaching forms of collective awareness that could help us understand and respond to environmental changes with unprecedented effectiveness. We might develop capabilities for coordinated action that could address global challenges that seem impossible today. We might even develop new ways of experiencing consciousness itself that transcend the boundaries of individual human awareness. But these possibilities also come with responsibilities that we're only beginning to understand. The fossil record shows that consciousness cascades during transition periods weren't just automatic processes that happened regardless of the choices made by the organisms involved. The development of collective intelligence required active cooperation, information sharing, and coordination among organisms that had never worked together before. The same appears to be true today. The collective intelligence systems that are emerging from human technological and social networks require active participation, conscious cooperation, and deliberate efforts to share information and coordinate responses to shared challenges. This means that each of us has a role to play in determining whether the emerging collective intelligence capabilities will develop in ways that help us navigate the challenges ahead effectively and ethically. The choices we make about how we use communication technologies, how we share information, how we cooperate with others, and how we respond to environmental changes all contribute to the development of these collective systems. The ancient fossil record suggests that the organisms most likely to thrive during transition periods weren't just the most adaptable individuals. They were the individuals most committed to contributing to collective survival and collective adaptation. They were the ones willing to share information, coordinate responses, and work together even when individual survival might have been easier to achieve alone. As we stand at what might be the threshold of another great transition, the lessons from Earth's frozen past suggest that our individual futures are inextricably linked to our collective capabilities. The consciousness cascades that helped life survive and thrive during ancient planetary transitions didn't happen because individual organisms became smarter or stronger. They happened because communities of organisms learned to think and act together in ways that transcended individual limitations. The same opportunity and the same responsibility lies before us today. The collective intelligence systems we're developing could help us navigate environmental changes that seem impossible to address individually, but only if we choose to use them as tools for cooperation rather than competition, for shared adaptation rather than individual advantage, for collective wisdom rather than distributed anxiety. The secrets buried in Earth's ancient ice don't just tell us about our planet's past. They illuminate pathways toward forms of collective consciousness and coordinated action that could help us create a future that's more resilient, more adaptable, and more capable of embracing the transformations ahead rather than simply enduring them. The great melt events that ended snowball Earth periods weren't just geological phenomena. They were consciousness-expanding events that opened up entirely new possibilities for what life could become. And the evidence suggests that we might be approaching another such opening right now, if we have the wisdom to recognize it and the courage to step through it together. The convergence of all these factors, the consciousness cascades, the collective intelligence networks, the reactivation of ancient genetic capabilities, points towards something that researchers are calling the integration threshold. This isn't just another evolutionary milestone. It's a moment when biological, technological, and consciousness evolution might synchronize in ways that fundamentally alter what studies have revealed something extraordinary about how information flows through living systems during possible for life on Earth. Recent quantum biology periods of rapid change. When organisms are under extreme environmental pressure, their cellular communication networks don't just become more active, they begin operating according to quantum coherence principles, allowing information to be shared instantaneously across biological systems regardless of physical distance. This quantum coherence effect was first discovered in photosynthetic systems, but researchers to be tapping into quantum information are now finding it in neural networks, immune responses, and even genetic expression patterns. During times of environmental stress, organisms appear fields that allow coordinated responses across entire ecosystems, almost interesting. The same quantum coherence effects that appear in stressed biological instantaneously. And here's where it gets. Really, systems are showing up in human technological networks during periods of rapid information processing. When global communication systems are handling large amounts of environmental data, when research networks are collaborating on complex problems, when social systems are coordinating responses to shared challenges, these networks begin exhibiting quantum-like properties that shouldn't be possible with classical information processing. It's as if the boundary between biological and technological systems is becoming permeable during periods of rapid change. The collective intelligence networks we're developing aren't just mimicking biological systems. They're beginning to integrate with biological systems in ways that create hybrid forms of consciousness and information processing. The ancient ice holds one final whisper, one last secret that connects everything we've explored tonight. As we stand at the threshold of what might be Earth's next great transformation, we're not just observers of planetary history. We're participants in a story that began 700 million years ago, when our planet first learned to freeze itself, solid, and emerge reborn. The consciousness cascades, the quantum coherence, the collective intelligence networks, they're all pointing towards something unprecedented, not just survival, but transcendence. The same forces that once turned Earth into a frozen marble and then unleashed explosions of evolutionary creativity are stirring again. And this time, we're here to witness it. But witnessing isn't enough. The fossil record is clear about one thing. The species that thrive during planetary transitions are the ones that learn to think and act together. As the integration threshold approaches, our individual choices about cooperation, information sharing, and collective adaptation will determine whether humanity becomes part of Earth's next evolutionary masterpiece or becomes another layer in the geological record. The frozen secrets have been revealed. Now, the question is what we'll do with them.